Welcome, everybody. I'm François Galère. I'm from EPFL in Switzerland, and I have the great honor to moderate today's PRF Journal Club. So today we have the pleasure to have Matteo Leonard with us from University of Liège. And he wrote a paper together with his advisor, Nicolas Van de Waal, on groove spacing and the way they govern water retention during condensation. So it's a great pleasure to have you for this journal club. So just on the housekeeping aspects, the idea is that you can ask questions during the talk on the chat only. You shouldn't interrupt orally. And at the end of the presentation, we'll have a question and answer session. So that being said, Matteo, the floor is yours.
Thank you a lot for the introduction. So today's talk will be mainly about condensation, a process that everybody has already encountered in his life, simply when you pour yourself a fresh drink during a hot summer. And basically what happened during this process, if the temperature of your substrate, so in this case the glass, goes below a certain temperature called the dew temperature, then naturally condensation will occur on the glass. The dew point depends on several parameters like the temperature of the air, the relative humidity of the air, and also the wind speed. It is a process that happens in a lot of situations, like in engineered system by humans. So basically in your air conditioning unit, you can have condensation as well as in the cooling tower that are connected to our energy plant. It is also a process that happens naturally during the night, and it is dew. So the water that you can have in your garden in the morning is basically comes from condensation. And we know that in our area we are facing more and more hydric stresses, and the idea is to know if we can try to capitalize on dew water to be an alternative source of water. So how do we collect dew water? It's quite simple. You simply take a flat plate that you put outside, and during the night there's a process called radiative cooling, so that the temperature of the substrate will go down way faster than the ambient temperature. And at some point, if the surface temperature of the plate cross the dew point, you will have nucleation. So for example, you can see an experiment that I've done outside, and in the early morning, you have condensation appearing on your surface. So this is quite an easy technique, but they have several drawbacks. And the main one is the yield, about 0.3 liter per night per square meter. So has to say a big glass of water. It depends on the season, so you will require high delta of temperature between the day and the night, and also longer night as possible. And you also need clear night. So here in Belgium, there is a lot of clouds, so it's not so effective, but if you go a bit southern, it happens more frequently. So now we look at only the yield, and we'll ask the question, can we try to enhance the yield of dew? To do that, we will do as many scientists before us, and we will look around us. And in nature, there are already a lot of tools that have been created through evolution. So for example, if you look at the cactus spine, you can see that there are tiny spines on the major spine, and we know that these tiny spines are a preferential nucleation center, and that the overall shape of the spine, so the conical shape, also passively transport water from the tip to the bottom of the pine. There is another example in this lizard whose scale arrangement around his head create grooves, and these grooves will also passively guide the water from his head toward its mouth. So in my case, I will add texture to the plate and look how it will change the condensation process. To do that, I will only choose one structure, and it is the grooves. And the main reason are that it is a robust and simple structure that we can arrange in array, and it's pretty convenient if you want to cover a full square meter of materials. And on the practical side, it is also fast to produce and affordable. So in my case, I simply used a laser cutter. So the question now is how grooves will influence the condensation process. To do that, I will first explain you my experimental setup. So how do I create condensation on my substrate? Then we will look at the dynamic on the smooth case and also at the collection of water on this case. Then we will add some grooves. And first we'll try to understand what's happening on this groove substrate. So you can see that here on the left, you have droplet that goes down on the substrate. And here you don't really see droplet, but you see kind of vertical line appearing randomly. And we will try first to understand what is the water dynamic on this substrate and then look at the collection. So for the experimental setup, I created an innovative setup, but I believe that everybody has already tried this technique at home, and it's quite simple. It's when you blow on a surface that is at room temperature. As our breath is moist and humid, it will trick the dew point so that it can create condensation on any room temperature substrate. So how do I do that in my lab? Simply with this experimental setup. So here there is a pot filled with water and I heat up the pot at 75 degrees. Then I will flow air in and it will at the base of the pot, and then it will create bubbles that will heat up and charge in humidity. And as I airflow in, there is also an airflow out, and this airflow will be directed toward the substrate. And this technique is way faster than the traditional technique to create condensation, that is the cold plate. Okay, so now let's look at the dynamic on the smooth substrate. So at the beginning, what we see simply nucleation and growth. And we can see here that all the droplets are static. And the reason is simple. It's because the weight of the droplet equals the retention force that originate from pinning forces, capillary pinning forces. If you now look at what is collected beneath the substrate, obviously you have nothing. Then if you let the experiment go a bit, now we see that droplet starts to move because the weight overcomes the pinning forces. And when they do that, they have in average a radius equal to 1 millimeter that we call the critical radius. And once a droplet reaches this radius, it will go down the sample, and doing that, it will collect all the tiny droplets that sit on this trajectory. For this reason, we call these moving droplets sweep drops because they collect the water. And if we now look, let's already the experiment go, we enter in what it seems to be a steady state. And if we look at the collection mass here collected in the scale, we see that the mass increases linearly with time. And what's really important to see here is that all the water that is condensed on the substrate will be collected through the sweep drop mechanism. Okay, so now let's look closer to the curves that I've drawn here. So as I said, there is a constant collection rate, also condensation rate, it's the same thing. And this is really important because it allows us to estimate the total condensed water on the system. So basically under these curves, it's all the water that you get on your scale. And in between the two lines here is the amount of water that is stuck on your sample. And that we call this amount of water the retention mass. It has two origins. The first is the water that is stuck on the vertical surface here, but there are also some droplets that hang below the inferior edge. In this presentation, I will only talk about the retention mass on the vertical surface. We can easily compute the mass of this droplet here and get rid of them. So now when I'll talk about retention mass, it is only about the water on the vertical surface. So we can plot the evolution of the retention mass as function of time. And we see that at the beginning, we have a linearly increased simply because we have nucleation and growth, but not yet transport. And at some point, water will start to flow down and we have a steady retention mass. So now we have the two main characteristics of our systems, the condensation rate and the retention mass. And we want to know how grooves will influence these two characteristics. So to do that, I will simply introduce groove. And to do that, I will do that, with my laser cutter. So grooves are spaced by a distance called S, the spacing. And the groove geometry, so its depth and width, in this case are equal to 0.2 millimeters, and it will be the same length scale for all the experiment after. So let's try first to understand what was happening on this substrate, and to do that I have to introduce three notions. The first one is the groove filling. So when you put some water in a groove, you want to know if this water will spontaneously move inside the groove or stay where it is. And asking this question is the same as imagining that you pull a bit the liquid inside the groove and look at the variation of energy when you do that action. In this case, what you change is only the interfacial energy. So, for example, previously the red region here, it was dry, now it is wet. And on the top here, the green region, previously there was nothing, and now you have a liquid gas interfaces. So all the variation of energy can be linked to variation in interfacial energies. And we can re-express this in terms of this variation of energy. And if it is negative, we will have spontaneous groove filling. So water will spontaneously go inside the groove. We can achieve this by two means. The first one is to choose the right materials. And in our case, we are playing with water, air, and acrylic. And if you want another means to impact the groove filling, you can also work on the groove geometry, because you see that depth and width also interact with the expression. And in our case, we can create spontaneous filling by adjusting the groove geometry, such as the aspect ratio of the grooves is superior or equal to 0.6. So that's the first concept. The second one, now we need to look up on our substrate. So what you have here is a different plateau. So the plateau is the smooth region between two grooves. And on the plateau, you see that there are some drops. Then you have a groove and other plateau. Now we have to look what will happen here at the base of the sample during the condensation. And what we saw here can be pictured here. So what we saw first is the upward groove flow, so the red zone that is rising up. And this groove flow is quite fast, about 100 millimeters per second over the entire length of the substrate, so 8 centimeters. Then you also see that at some point there can be contact between the plateau droplet and the grooves, and that will lead to an important chain reaction mechanism, because droplet will be absorbed by the groove flow, and it will help the groove flow to be propagated further away inside the groove, and raising the likelihood to create new absorption mechanism. So what's really important to see here is that at the beginning we have isolated droplet sitting on the plateau, and at the end you have a full liquid network that is connected by the grooves. At this point there is no transport as such, it's simply fluid reorganization around the groove. And this is called the drying process. Then it is the third thing called the long-range coalescence. And here we have to dezoom still from the sample. So what you see here is the full height of the sample. And what we see is the inflow propagation, the droplet generation astride the groove, that is simply the water reorganization. Then we see that some droplets are pumped inside the groove, whereas some other can grow big enough to shed on the surface. So let's once again decompose what we see. So the blue arrow here is the fast inflow propagation. Then we have the reorganization of fluid on the groove. And then we have fluid exchange through the groove by pressure, either hydrostatic or either Laplace, so either by gravity or either by geometry. And that will lead to hierarchical pumping. So higher droplet will be pumped first inside the groove. And then we have transport in two modes, either by the groove, so as this droplet is being pumped by the groove, but you can also have sweet drops if some droplet get big enough to shed like on a smooth surface. So the reorganization took about 1 second, whereas the full transport along the groove took about 10 seconds. Okay, so now we have all the key ingredients to understand what was happening on our groove substrate. First, we selected the right aspect ratio to allow impregnation. Then the drying event creates sudden vertical line, and what we see is simply the fluid reorganization around the groove, as well as the inflow propagation inside the groove. And finally, there is the long-range coalescence transport that will help collect the water and get it down the grooves. And it is the combination of these three things that can be defined as the groove transport. Okay, so that was for the dynamic. Let's now look at the collection. So now I will present you the amount of water that is collected beneath the substrate as function of time for the smooth plate here in orange and the groove plate here in green. And what we see first is that we have the same condensation rate. And that's a pity because the condensation rate is the major lever to try to increase collection, but it is not so much a surprise that is the same. In fact, the condensation rate is constrained by thermodynamic, and if you wanted to influence this condensation rate, for example, you would have to change the temperature of the air that you blow on your surface. So that's what I've done here. Okay, so groove have no impact on the condensation rate. What about now the retention mass? So the amount of water that is stuck on the plate. And here we see that the smooth substrate gather more water on its surface than the groove one. So let's try now to be a bit more systematic and let's study the retained mass on the sample as function of the groove spacing. And it is represented here. So here on your right, you have the smooth sample. And then when you add some grooves on your sample, first it will increase the retention mass up to 70%. And then if you still continue to add groove, at some point you will also decrease the retention mass down to 20%. And we see that there is an inversion about a spacing equal to 1 millimeters that is near the critical radius of shading on a smooth surface. So what we see is that when we pattern our surface with parallel groove, the spacing of these grooves can fine-tune the retention on our plate. So let's try to have a bit of intuition on what's happening with these two behaviors. When you consider distant grooves, like here, the sweep drop mechanism is the dominant one. So in average, the grooves are inactive, and we can assume that there are only water that is stuck inside the groove. So the more groove you add, the more retention you have on your substrate. Whereas when you consider the closed groove system, now the groove transport is the major one, and grooves are really active. So the retention now shifts from the groove toward the plateau. And on the plateau, the droplet size that sit on the plateau is proportional to the plateau width. So the smaller the plateau width, the smaller the droplet, and then the smaller the retention, as you can see here. And how to interpret now the increased retention mass at intermediate spacing? We can explain it by a transport conflict, because at this spacing, droplets are stuck on the plateau. They are too small to simply move by gravity, and they have to wait a groove transport to be evacuated. But as the distance between two grooves is also important, it takes more time to be evacuated by the groove. So at this intermediate spacing, you simply have two bad transport modes. And this leads to increased retention. So in conclusion, I presented you an experimental setup that is innovative in the way that is way faster than the traditional method. It allows us to visualize groove transport, whereas it also allows us to explore a lot of parameters in a really rapid way. Then I introduced groove, and we saw that introducing grooves with specific spacing allows us to fine-tune the retention mass on the substrate. And this retention mass is reminiscent of the interaction between the groove transport and the sweep drop transport. Unfortunately, we don't have an impact on the condensation rate, but we now have also a control on the droplet size because they are stuck on the plateau. As perspective, it could be really interesting to modelize the groove transport. So here I only described it, but I don't have modelized it. And once it's done, it would be also interesting to integrate this modelization into the retention mass modelization. We can also look at more complex patterns. So here, for example, I've created convergent groove. And we see that with this type of grooving, we can now decide where the water will leave the surface. And there is a problematic that a lot of people face in thermodynamic. It's the film-wise condensation whose heat transfer is really bad. And maybe that with the interaction with groove transport and sweep drop transport, we can now try to prevent film-wise condensation. Finally, we could also look at heat transfer, and we know that the heat transfer coefficient during condensation is proportional to the droplet size that sit on the surface, where bigger droplet leads to smaller heat transfer. Now, with patterning, we saw that we can control the size of the droplet, and it could be also interesting to see if we can have a control on the heat transfer parameters of our surface through the grooving. And with that, I would like to thank you. And if you have any question, feel free to ask.
Thanks very much. Any questions in the audience? So maybe I can give it a start. I was a little bit, it's a technical thing, but I was a little bit surprised by one of the curves that you show when you have this sort of regime at low groove distance. Can you show this curve where you have the two behaviors? Yes, this one. So on the left, it seems that the curve is first going down and then up.
Yeah, the reason is quite intuitive. If we look at this picture, so basically what you consider here is getting closer and closer groove, but at some point, the plateau in between will disappear. And if you continue to get groove closer, it's like you get a smooth surface back, because too much grooving is getting a smooth surface back. And if you look at I haven't put the model here, but if you do the extrapolation on the model, you can see that this curve will go back to the smooth case. Up, I don't know where it is. Yeah, it will go up to the smooth case. It will make the junction.
I see. Thanks a lot. Very clear. There is a comment on the chat, a question. So first a comment. So Joe West says grooves look like the leaves of a corn plant. Very good at condensation as well, as I learned when detasseling corn in the summertime as a kid. So I don't know if you looked at corn plants, at leaves of corn.
Not that much. I've done only experiment in my
maybe
lab.
it's just worth having a look. And the second question still by Joe West, how long does it take to print one of the sample plates?
About 1-2 minutes. It's really fast. So to pattern the surface, if I get the question right, it's really fast. It depends on the amount of groove that you make on your substrate. So yeah, to be fair, it goes between, I would say, 1-2 minutes to maximum 10-20 minutes for the heavily grooved substrate.
Okay. More questions?
I have one question. Can I ask?
Sure. Go ahead.
Yeah. During condensation, the latent heat released, it will go to the condensing surface. And for a stable condensation to happen, so the condensing substrates need to be cooled so that we get a substrate temperature below to the dew point temperature, as you said. So how you are maintaining the substrate temperature to a particular temperature?
Yeah, that's a good question. So in fact, I'm doing my experiment in a big climate room. So it's about 3 meters over 4. And this room has temperature control. So it's controlled at 21 degrees. And there is a big control on temperature with air renewal that leads us to have control on. I don't have control on the temperature of the substrate, but the heat from the substrate will go in the room and the room is cooled.
Okay.
Does that answer your question?
Yeah, I got it. I have one other question. So in principle, when we grooved, so the condensing substrate area increases as compared to the flat surface. So what's the explanation? Okay, though we are increasing the condensing substrate area, but we are getting the same amount of condensate as you have shown in some graph.
Yeah. The fact is that if you want to pursue condensation, you need to get rid of latent heat of condensation. And raising the surface won't help to evacuate heat because heat comes from the face on the surface. So it does not change that much to increase the surface because the heat can only be released by the back of your sample, and the back is flat in all cases. So there is not heat released from the front of the surface because it is the part of the substrate that is under the heat and moist airflow. I don't know if it's can maybe show.
Okay.
Yeah, here. So the airflow goes on one side and the heat goes out only from the back of the sample, not from the front, because in the front you have this really hot and humid air that comes from. So you cannot really release heat from that part.
Okay. The condensing area from where the condensation is happening. So the groove is there only, na?
Sorry?
The grooves are there only where the condensations are happening.
Yeah. Yeah, so I don't know if you can see, there is grooves on this side, but here it's flat.
Got it, got it. Backside it will be flat, but where the condensations are happening, there are the grooves.
Yeah,
So
exactly.
effectively we are increasing the condensing area, though we are getting the same amount of condensate as we are getting on the flat surface.
Yeah, because what would be interesting is to increase the area of the cooling surface. But here it's not the case. The cooling surface is the back of the sample and it's smooth in all
Okay,
cases.
okay. Got it, got it.
Thanks. There's another question in the chat. Beautiful presentation. This might be something I missed during the talk, but what is the groove size also studied as a parameter? And what are your thoughts on what happens if we make smaller grooves?
Okay, so really nice question, thanks. So the groove size are about 0.2 millimeters on 0.2 millimeters. Here, so they are not that big. We can change the groove size, but you have to stay in a certain range of aspect ratio because if the aspect ratio is too shallow, you don't have a groove filling, so you will simply have like big droplet appearing on your surface as on a smooth surface. So you need a minimum groove aspect ratio. And then the deeper the groove, then you will also have influence on the groove transport. And for that kind of question, it's more technical because there is not yet theoretical explanation of the groove transport. So the dependency of the groove geometry on the groove transport is still an open subject in this area.
Thanks. I also have another question which is related to what you mentioned about film condensation, which you would like to prevent. Do you think that this groove design will help preventing film condensation? Did you have cases where the smooth plate would end up in film condensation, but the grooved one would not?
So in my case, the experimental setup wasn't strong enough to create film condensation on my substrate. So I didn't have the opportunity to test it, but I thought intuitively that as now we are dealing with two modes of transport, maybe we can break the film formation thanks to the groove. Because it will divert, some part of the fluid will be diverted inside the grooves. And so there is less fluid available on the smooth surface so that we can maybe break the film formation.
I see. More questions?
I have probably maybe two questions. My first question is that over in the videos I saw, like in some cases the droplets which are falling down, like they kind of coalesced, and in some cases it didn't. So I was just wondering, like, is there any
Sorry,
particular
could you
set of
repeat?
so in some cases, like I saw that the droplets kind of coalesced, it formed like a bigger droplet before falling, whereas
Yeah.
in other cases it didn't. So is there any set of parameter scales you kind of uh, uh, govern to kind of make sure that sometimes like is the coalescence kind of an interesting property for you to look into it, or is it like is it possible for you to control whether the coalescence happens or not?
So you're right to point out coalescence because here I made it a bit easy, but in reality it's more complex than that. There is no one droplet that grow big enough and then shed. often you reach the critical radius through a coalescence. And it is a really complicated situation because in this case, there are a lot of droplets that can merge with a lot of neighborhood. And there is not yet a theoretical background on this collective phenomenon. But surely coalescence are really important in this case. But I was not able to, it was not the aim of this work to look at it. But I believe on smooth surface, we still have a lot of work to do thanks to coalescence.
Okay, thank you. Also have another question. Like in the prospective slides, you're talking about complex geometry form, right? So in that sense, like I guess you're looking into instead of it being a vertical, yeah, probably this one should be good. Like the last one is kind of like so here you're kind of varying the angle at which it you're making the groove, and then you're trying to see if two grooves kind of combines to form a channel, and then is that what you're trying to do in the last
Yeah, so
pattern?
you have groove flow inside the inclined groove, and this flow will then be redirect inside this major vertical groove. So that, as you can see here on the smooth surface, water comes from everywhere on the surface, and it ends up where sweep droplets end. Whereas on this case, as all the water is channeled inside the groove, it has only one exit point, and it is this one.
Okay. So that means like in the future prospects, you're also interested in making it more complex by adding more kind of channels, like in a sense, like now it's like two
Yeah.
cross sections, not then you are also interested in four cross sections or something like that, or is it something like that?
Sorry, what was the last part?
So my question was that I guess here your angle of inclination is one parameter you're going to introduce further to make it more complex, right? So in that
Yeah.
sense, uh, uh, my question was that now it's like two channels which are combined to form one particular branch kind of thing. So then are you also interested in making it like four uh, channels, like four grooves combining to form one particular channel or something like
Yeah,
that?
you're right. So you can change either the inclination of the secondary channel, but also the width of one, here it's a pattern, we would say. You can also change the width of one unit of these, for example.
Okay. Thank you so much.
With pleasure.
Great. Is there any other question? We actually already run slightly over time, which is good news. It shows that this was really a very exciting and very interesting paper with a lot of simultaneously new observations, but also open ideas floating still. So this is extremely convenient or ideal for these sort of journal clubs. Very stimulating. So I think
hope it was clear for you.
It was. So I think we can probably wrap up there, unless there is a last burning questions on the chat. Okay, there isn't. So Matteo, I'd like to thank you a lot for this beautiful presentation, and let's look forward for the next journal club in a month.
Yeah, thanks a lot for the invitation.
Bye bye everybody. Thanks for joining.
Bye.
Bye bye.